All right, welcome everybody. We are here to talk about real-time data at the edge with Amazon SageMaker NVIDIA GPUs. We're going to talk about how you build all the tools needed to build a video analytics pipeline from front to back, and hopefully you'll leave with an understanding of how all these tools work together and how you go about constructing such a thing. My name is Ryan Vanderwerf. I'm a Partner Solutions Architect here at AWS, and here from NVIDIA is...
I'm Eddie Weil. I'm a Senior Solution Architect at NVIDIA, and I'm on our team supporting AWS and Amazon.
And Yushin?
I'm Yushin Yang. I'm from AWS Professional Services, working with customer across the industrial, across different industries, such as industrial customers or computer vision or predictive maintenance. Great.
Thanks, everybody. So let's get started. So here I'm going to show you a video of the front of my house here. This is my father taking out the trash while I'm away. And you can see here what we're doing. This is a video analytics pipeline. We've got two bounding areas where we're counting people going in and out of my house. So one counts it one way and one's the other. And you can see there's an arrow pointing each direction. So basically, at the end of the day, we're going to have something, show you how to build this and all the tools needed to build this. So you can do this with your own setup. All right, we're going to talk a little bit about what kind of problems we're trying to solve with these. We're going to show you some of the hardware that we use to do this at the edge with the NVIDIA Jetson. Eddie's going to talk about NVIDIA TensorRT and DeepStream. These are some of the tools that you use to build these things. We're going to talk a little bit about AWS IoT Greengrass 2. We're going to use that to deploy these to the edge devices and manage the deployments. And then we also talk about Amazon SageMaker Edge, in particular Neo, where we can do optimization of your models and then deploy those to the edge. And then we'll show you how we put all that together to build a people counting application. All right. Take it away, Eddie.
Thanks. So, hi everyone again. So I'm going to be talking about kind of the NVIDIA stack as we build through our application. So we're going to be talking about AI inference here. So we can think about many different types of AI inference. So it can be computer vision, it can be natural language processing, it can be recommendation systems. But the kind of key factor here is we need to deploy all of those models somehow. And we want to do that as efficiently and as optimally as possible. So today we're going to focus on computer vision, but some of the same techniques and things can be used for conversational AI, recommendation systems, and everything else. So one of the things that we want to keep in mind whenever we're deploying these types of models at the edge is a number of things. So the first one is going to be the complexity of these neural networks. So you can think of 5, 6 years ago, all of these were relatively small, so we could just take the neural network for image classification and run it on something like a Raspberry Pi. As the models have gotten bigger and bigger, we can't do that. So specifically with things like big text or big speech models now, we actually have to optimize those to be able to get them to run on some of these edge devices. The second complexity here is actually trying to build a full stack. So in most cases, you don't actually just want your neural network to take an image and give you some sort of classification. You want to build an entire pipeline around that. So that includes things like pre-processing, post-processing. Usually you have to do things like dewarping or something like that if you have full video streams coming in. So all of that has to be taken into account. And the last one, which is where we're going to focus most of our effort today, is deploying and scaling that to the cloud. So you want to be able to not only run your neural networks at the edge on the devices that we're going to talk about today, but also be able to scale and take your metadata, put it in the cloud, do some processing there. So the first thing we want to talk about is the hardware that we're going to use. So I'm going to be talking about the NVIDIA Jetson. So you can think of it kind of as an entire platform. So not just the hardware, it's everything that you see here. So of course it's the hardware that's kind of underneath everything that we're going to talk about. But we also have one of the most important parts is software. So I'm not sure if people know this, but about 80% of NVIDIA is actually software engineers, believe it or not, even though we're a hardware company. So software is a huge part of this entire ecosystem. And the last one is working with other people, so partners in our ecosystem. So people that actually build solutions around the Jetson with our software stack. And all of this together is kind of the NVIDIA Jetson platform. And what the hardware actually looks like is something like this. So we have an entire family from our smallest Jetson Nano all the way up to the big stuff that's powering some of the robotic solutions that you've seen here. So all the way down at the left side, we have the Jetson Nano, and that's going to give you about half a teraflop of FP16 performance. And you can run that anywhere between 5 and 10 watts. So it's relatively low power for an edge device. And then we have the TX2 series and the NX series in the middle, and those are kind of more mainstream. And those a little bit higher power, but what that gives you is the ability to run larger and larger AI models. And then on the far right, you can see the AGX Xavier series, which is kind of the flagship product we have for Jetson. And that's going to give you the most performance out of this entire family. And then recently, on top of that, we recently announced the Orin series. So we have the Orin NX and the AGX Orin. So one of the cool things I want to point out is the performance differences that we have here. So the AGX Xavier on the bottom will give you 32 teraops of performance, which is really, really good. You can run multiple AI models with that. But if you want to scale that up to run tens of AI models or hundreds, depending on the size of them, you can go to the AGX Orin, and it gives you 275 teraops. So almost a 10x improvement. And one of the things that I mentioned earlier was the importance of software. So not only is the hardware important, but everything that sits on top of it. So at NVIDIA, we have a couple of different things that I want to point out. The first one is AI model development. So we have pre-trained models that allow you to get started quickly with your application. So things like object detection, classification, like that. We also have TAL Toolkit, which I won't cover too much here, but basically you can take a pre-trained model and train it for your use case. So you can take an object detection model, take your data, and train it for that. And then we have application frameworks on top of that. If you're building for, say, a robotics application, you can take the Isaac SDK and actually get started very quickly with some of these devices. One of the other ones that we'll talk about also is DeepStream. So that's kind of our video analytics pipeline. So that's the back end to what we're going to be building today. And then the last piece is the Jetpack SDK. So that's what everything is built on top of. So the software packages that make everything work. So this is what the Jetpack SDK looks like. So this is the software stack that you'll get whenever you get a development kit or a Jetson module. Whenever you download the Jetpack SDK, this is what's going to be included with that. So at the bottom, we have what we call CUDA, and that's basically the programming language that you're going to use to interact with that GPU. And then we also have libraries right above that that kind of make it a little bit easier to interact with that. So there's cuDNN, which is basically accelerated deep learning for, that uses CUDA underneath. And then we have things like cuBLAS and cuFFT for linear algebra and fast Fourier transforms. And then we also have things like OpenCV that's been GPU accelerated. So if you already have an OpenCV pipeline, you could use something like this, and it would be GPU accelerated. And then on top of that, we have our SDKs. One that we'll talk about today is the DeepStream SDK. And then on top of that is all of the ecosystem partners. So everyone that's building solutions on top of this entire stack. And just a cool little demo that I wanted to show before we move on. So a lot of you are familiar with object detection or image classification. Those are pretty standard types of models. So at the top left, you can see 4 different video streams being processed with object detection. Actually, they're doing classification there too, as well as people counting. So all of that is happening up there at the top left. In the top right, we have a text question answer model. So basically, we're given a passage, given a question, and it's running through that model trying to answer that question. On the bottom left, we have pose estimation, and on the bottom right, we have gaze detection and facial recognition. So the reason I show this video isn't because of all the cool models that are running there. the reason I show it is because all of this is running on a single Jetson. So not only can you run tens of the same computer vision model, but you can also run multiple different models at the same time, depending on what you need. Obviously, most use cases wouldn't need all of this at one time, but you could use mix and match as you needed. So now that we've talked about the hardware, the next thing is to talk about optimizing our deep learning model. And for that, we have TensorRT. So one of the most important things that we want to think about whenever we're optimizing models is the complexity and the things to keep in mind whenever we're optimizing models. So obviously, you want your model to be as accurate as possible. You don't want it to misclassify a dog as a cat. But also, you don't want to wait 35 seconds for it to classify a dog as a cat. So all of these things have to be thought about whenever you're optimizing a model. And that's where TensorRT comes in. So what it actually does is take a model from any of the popular frameworks, so TensorFlow, PyTorch, MXNet, take your pick, and optimizes that model as best as possible for the hardware that you're running on. So this could be a data center GPU like an A100. It could be our drive platform, so inside of a vehicle, or even what we're talking about today, the Jetson devices. So TensorRT works across the board for all of those. And what it actually does is take your trained model, convert it to what we call an intermediate representation, or in this case, we're using Onyx, and then takes that model and runs it through an optimizer. And one of the cool things about that is it's relatively straightforward to run through this optimizer. The problem comes into play if you have a very specialized model. So TensorRT doesn't understand every single custom layer that could be developed ever for deep learning. So that's where the second part comes in, so the TensorRT framework integrations. So if you're using PyTorch or TensorFlow, you can actually just add a single line inside your TensorFlow or PyTorch code to use TensorRT. And this is kind of what that looks like. So if you're building a PyTorch model, typically you just put it in eval mode, and then you can run inference that way. But all you would need to do is actually do this torch trt.compile, and that's going to turn it into that TensorRT engine file. There are some caveats to that. One of the caveats is that if there's layers inside that model, like I mentioned, that aren't supported, then you can't convert that entire model. The advantage, though, of keeping it in the framework is actually being able to compile that model. So what actually happens is the compiler will go all the way through the model, basically take a look at all the layers that are inside that model, and anything that's supported by TensorRT is going to be converted into this TensorRT engine. Anything else is going to basically fall back to the framework. So it's going to have the same performance, same speed, same implementation as we had before. So these are kind of the comparisons between the two. So like I mentioned, if you stay in the framework, if you just run inference with your TensorFlow model, it's going to support pretty much any model that you can throw at it, because TensorFlow supports all of those for your training process. But the problem is there's no GPU specification, there's no optimizations there for GPUs. So it may run on a GPU, it just may not run well on a GPU. The next one here is the TensorRT framework integrations, which we just talked about. So that's going to be a little bit faster, but again, remember, if we can't convert that whole model, it's still going to fall back in some places to TensorFlow or PyTorch, whichever framework you're in. And then the last one is converting it all the way to TensorRT. And this is the most optimal option. But again, if you have layers that aren't supported, sometimes it's difficult to get it all the way to TensorRT. So there's kind of trade-offs going in between each one of these. And just before we move on, I wanted to point out some of the things that TensorRT is actually doing. So to make your model more optimal, one is layer fusion. And basically what that's doing, so the model at the top is basically a part of a transformer model. So if you're familiar with BERT, this is a portion of what's inside that model. And what we're doing with layer and tensor fusion is actually taking some of the like operations and fusing them all together. So I guess in the long scheme of things, what that actually does is makes less calls to the GPU meaning that you're actually going to be transferring less and less data back and forth between the GPU and the CPU. Also, we can basically fuse all of those together, and we have less and less kernels because we're actually doing less and less operations on larger and larger data. So all of this is going to speed up the pipeline for optimizing our model. And then the last one here is kernel auto-tuning. There's a few other ones, but this is the one that I wanted to call out. So basically, we have a whole host of different GPUs. So we have data center GPUs, the drive GPUs, all the Jetsons. What kernel auto-tuning does is actually take your model, every single operation, and look for specific specialized kernels operation for the hardware that you're deploying on. So think about a convolution. If you deploy on a data center GPU, the CUDA code that's running on there is going to be slightly different than what you would deploy on a Jetson. And what TensorRT does underneath is actually goes through all of those and tries to find the most optimal one. So now that we've talked about optimizing the model, we want to take that and actually deploy it. So that's what we want to talk about DeepStream for. So this is what we think about whenever we visualize what a typical video analytics pipeline would look like. So we have all of our incoming streams, whether that's video, some kind of sensors, microphones, things like that. And we have to capture it and decode it somehow. And then after that, we have to pre-process it, batch it, get it ready for whatever AI model that we have. And then we run AI inference, potentially some tracking if we're using it for a vision application. And then we want to do something with that data. So extract metadata, visualize it, do something like that. So typically what you would do in this scenario is use something like GStreamer. So you could take, each one of these pieces can be developed with a GStreamer plugin. So what we've done at NVIDIA is actually created a platform that you can use GStreamer kind of underneath, and all of these pieces be GPU accelerated. So what that looks like is whenever you're running pre-processing or whenever you're running your AI inference or tracking, all of these things can be GPU accelerated with DeepStream. So it sits on top of GStreamer, but you can develop plugins the same way you would for GStreamer. So what's the advantage of actually having all of this on the GPU? Obviously, if it's enough workload, it's going to run a little bit faster. But one of the biggest benefits of this is actually not copying data back and forth between the GPU and CPU. One of the biggest parts of my job is actually profiling customers' code and trying to find the bottlenecks where we can speed it up. And one of the biggest things that we find is unnecessary copies between CPU memory and GPU memory. So underneath the hood, DeepStream is actually taking all of that and obfuscating it away from you. So once you move data onto the GPU, it stays there through the entire process, so there's no copying back and forth. So once you decode it, once you batch it together, AI inference, all of this stuff is done on the GPU. And then you can transfer back whatever you need, metadata, things like that. So that's one of the huge benefits of using DeepStream. And this is kind of what the SDK looks like. So from the bottom, you can see all of the hardware platforms that we've talked about so far. On top of that is the CUDA platform. And then on top of that is the DeepStream SDK. So what comes inside of that is basically a set of accelerated plugins. So if you're familiar with GStreamer, it's the idea of putting together plugins into a pipeline like this. So you can think of these as GStreamer plugins that are built to run on a GPU efficiently. The next thing is pre-trained models. So one of the biggest things that we have at NVIDIA for your disposal is actually taking a so you don't have to, I guess, use your own data to go through that training process. Obviously, you can take it and retrain if you have a little bit of data, but in that case, it would take hours instead of days to get a model that would actually work for your use case. One of the other things here is over-the-air model updates. So for example, if you had an object detection model and wanted to update it, you did some more training and noticed that your new model is 3, 4, 5% better, you can actually do an over-the-air update to that device and instead of having to take down the whole service, you can over-the-air update that model. And then on top of that, we have basically how you interact with DeepStream. So you can do that in C and C++, which is kind of the native way to do it. We also have a Python API that you can do that with. And one of the newest features in our newest DeepStream SDK is this graph composer. So basically that gives you the ability to kind of build your pipeline in a visual way. So instead of creating a configuration file or writing a Python script, you actually drag and drop these blocks to build your video analytics pipeline. And I wanted to close with this before I hand it back off to Ryan. So this is kind of what we're going to be building today with a little bit of changes. So we're going to take in a video stream or multiple video streams. We're going to decode that and multiplex it so that we can actually use it. And then we're going to be running it through this primary detector, which is going to be detecting the people moving in and out of the house. And then the secondary classifiers here can be thought of as the neural net or whatever that's doing the counting. And then obviously the big part here that we want to talk about that I'm going to leave to Ryan is the message broker part. So that's how we get all of this metadata and things to the cloud. So with that, I'll hand it back off to Ryan.
All right, thank you, Eddie. So how do we get these things out to the edge devices, right, and not have a big tangled mess of trying to deploy things and doing all that by hand? Say I've got hundreds of these units maybe out in the field or thousands somewhere, and I want to push new models out or new code that runs on those models. I need a tool to do that. So we have AWS IoT Greengrass to help you do that. And basically what we're going to do is give you some tools and a framework from the cloud to manage a fleet of devices. And what you can do with that is, gives you the ability to have these local messages and triggers that can go from the local device back to the cloud. Again, via that message broker Eddie was talking about, we can send MQTT messages back to IoT Core in the cloud and then take actions on them. Say you want to send an alert to someone that goes on call that something odd's going on or something's performing very badly. Or I can just put that in a time series database and accumulate some analytics over time. Other things you can do is you can keep track of the state of the devices. Say they're intermittently connected to the cloud. If the device goes offline, it'll keep running without needing an internet connection. And when it comes back, it can change that data state and synchronize all of its status back from whatever the cloud was trying to ask of it for the time it was offline. You can also do your own choice of runtime. So you can run AWS Lambda, like you did with our old Greengrass platform. But you can also just run a Docker container or an OS native set of shell scripts, Python scripts, a Java application, any kind of application you really want. And it even runs on Windows. So you even have a lot more options now than you've ever had. And again, we're going to run this ML inference on it. And then if you have large bits of data that you need to go back to the cloud, you can run Stream Manager as a plugin. And so what that'll allow you to do is a Kinesis data stream and take a heavier amount of data back that doesn't fit into a 128 kilobyte MQTT message. And you can also have things like Secrets Manager, where maybe you want the device to access something in the cloud, but you want those credentials to be temporary. So say if someone got a hold of the device and ran off with it, by the time they get it and boot it up, they wouldn't be able to get into your account and do anything because all of the tokens would be expired. All right. Some of the other advantages of using Greengrass to deploy all of your things to it is that you've got this remote fleet management. You can deploy to groups of devices. So you'd usually categorize things by a group and then deploy to all of us at once. And you can even set it to where if I do a new deployment and say I want new models or new code out there, for one or two of them aren't successful, that's fine. We'll go ahead and roll back the ones that weren't successful, and you can go back after the fact, see what happened. You've got the ability to do these over-the-air updates of Greengrass itself, so it can update itself when you push out, and you can build these own custom components. So we have a format called, we call them recipes, and they can be in either JSON or YAML format. They're pretty simple to do, just a shell script, and it's got some lifecycle commands to do that. And again, we've also got some local development tools. So if you're developing these things on Jetson devices, you can just run deployments locally, not have to take the round trip of the cloud, debug your application and see what's going on. help you iterate in development a little bit faster, and then go ahead and start deploying from the cloud once you're at a comfortable state. So this is what the edge runtime looks like. This is kind of the components of a Greengrass component that I'm going to push out to the Jetson platform. So I could choose which plugins I want. So it'll only use which plugins you need. So if you want Lambda support for, say, legacy types of things, or you write like Lambda code that you were testing in the cloud first, you can deploy that as a component, or Docker. I can do simple shell scripts or an operating system process, or any other runtime that you want to bring along with it. You can go ahead and do that. As long as it can execute on your target device, you can make that work. And then once that deploys out, it will go ahead and run it through an installation lifecycle, then a run lifecycle, and then your code's running. All right. So some of the things here we can do with SageMaker Neo is this is a runtime that's running on top of TensorRT. And so when you're using SageMaker and you have your models developed and you want to run those to push them to the edge, we have something called a compilation job. And this is something that's part of our SageMaker Edge Manager platform. And what it'll do is compile your model to work for the target device that you want to do at the edge, and then optimize it. And then you can go ahead and push that down either with Edge Manager, or you can push that down with Greengrass. And some of the reasons that you might want to do this is maybe you want to deploy to multiple platforms that aren't all Jetson. Maybe they're Drive platform, or maybe they're just something completely different. You can still have that same framework code running in SageMaker and have those compilation jobs targeted to deploy to those types of devices without you having to manage all of those things yourself manually. So that kind of takes a lot of the pain out of deployment and building models and then getting them out to the edge devices. So part of our tool is called SageMaker Edge Manager. It will also help you manage the models of the devices. You can use this to deploy the models to the edge. And what happens is, while the models are running, it's actually sending feedback back up to SageMaker. So if you start getting like model drift and things start getting off, you can account for that and then automatically tell it to push new models back out once you've retrained on new data. Maybe it's a seasonality change where things aren't working as good visually as they used to. You should be able to catch that with Edge Manager, get that, and then push it back out again to all your devices. And so how does SageMaker Edge Manager work? Well, we start with our SageMaker, run and test, make sure everything's working good in a notebook or in the studio. And then we compile the model for the edge, which will then package that up. And so what it's doing in there is packaging up our model and the SageMaker runtime for Neo. And it's going to put that out on your edge device. So when your code runs, it has everything it needs to start up. And then from there, what's going to happen on the Jetson device when you're deploying and running it is it's actually going to use the TensorRT as well. So you're having both, you kind of have the advantages of both things going on there. And then again, for that maintain cycle, you've got that metadata going back to our service to help you account for things like drift or changing conditions. I'm going to hand it over to Yushin now, who's going to talk a little bit about the details of doing this.
Thanks, Ryan. So now we are down to the implementation level of how to actually implement these compiled model to your edge device. So this is the first strategy that you're seeing. You basically directly take your Neo compiled model and then use AWS Greengrass to download that model to your edge device. And then use DeepStream application to load that model into NVInfer plugin, and that plugin integrates well with our Neo compiled model. It's a shared library, basically. And then this plugin you can build, you can do a make file, and then put that, you can put that Neo shared library, compile that together with the NVInfer plugin. And then that NVInfer plugin can be called by your DeepStream application, and that runs seamlessly with the rest of the DeepStream application layers. And so this is the first strategy to implement this. And now you may also wonder how it works with SageMaker Edge Manager. How many of you have worked with Triton before? So Okay, I see a few hands. This is very similar to Triton, and it uses a gRPC protocol. Basically, from your DeepStream application, you still have that NVInfer plugin, and within that plugin, you make gRPC calls to this Greengrass maintained SageMaker Edge Manager agent. And so you can see that orange line in between, so that's talking in gRPC. You put your tensor, you store that in your unified memory in your Jetson module, and you pass that memory pointer through gRPC protocol to Edge Manager, and Edge Manager, after running the inference, is going to put the inferencing output back in your memory, and your DeepStream application continues from there. So these are the two strategies where you can integrate your DeepStream application together with AWS services. And now this is a detailed implementation of how this NVInfer component is a DeepStream component. And underneath there, you integrate with this made shared memory file, and that shared memory file is going to further integrate with AWS DLR runtime, and then call your model and ask it to run inference, and then so you can communicate back and forth through either gRPC, or if it's Neo, then it's easier. It's just the single process. And now it is demo time. So we can quickly show a video of how we deploy. We first compile a Neo model and then deploy that to your edge device. So I'm going to start playing this video. And for the sake of time, I'm going to jump through. We're going to skip through a few frames. But this is the repository that Ryan and I actively maintain. So it's also open source. If anyone see any problem, just file a pull request. We're going to review and update. And currently, we have tested with Jetpack 4.6. And so first of all, you navigate to Lab 1, and there's a Jupyter notebook that you can go through. It's a demo. It shows you how to pull some existing model, and then it's just a YOLO v3 model with people detector, basically. And then the notebook is going to tell you how to compile it through Neo, and then and how to, let me see. Where is that notebook? Yeah, this is a notebook. So you install a bunch of libraries, and then it is going to show you how to compile that model through AWS Neo service. Basically, you need to configure a few configurations regarding the NVIDIA accelerator, such as what is a TensorRT version, what is a CUDA version, the GPU code, and GPU code is which Jetson device that you're running inferencing on. And so once you configure all of these, you just start a compilation job. After the job is finished, you can see there is a status saying complete. You navigate to output, and then you download the model. The model is going to be stored in S3, and then you just download your model from there. I think it's back. And now you navigate to your Jetson device. And you first clone the repository that we have prepared for you. And I'm going to skip through the demo, but for anyone who is interested, this material is also available online. So after you clone the repository, you can see this DeepStream occupancy analytics file. And in there, there is a compiled shared library which you can use, and it is just a DeepStream NVInfer plugin that can be directly used by your DeepStream application. Now, let me skip to the output, which is the most exciting part. So this is still Ryan's house, and this is the original video that we saw earlier. And now in a while, you can see the output of of the DeepStream application. Let's see. Yeah. So you can basically overlay 2 threshold lines, and whenever a bounding box of a person walk past any of the threshold, you can see the entry number actually increases, or based on which direction that the people are moving. So yeah, that's it. That's the demo. Now I'm going to hand it back to Ryan to talk more about the rest.
Okay. So again, check out the GitHub repository there. There's also some blogs here that we can see. And so you'll want to see if you can check those out, get a little more information, get your hands on, and try some of these things yourself. So I'll talk a little bit about a couple of the other tangential services that we have that also run on Jetson devices. So we have another service called Lookout for Vision. And what it does is it enables people to do quality control and detect anomalies on things like manufacturing lines and assembly lines. And these go ahead and also using Jetson, you can integrate with Greengrass, and it will deploy out models that you would normally run in the cloud to the NVIDIA edge devices. And so now I can do that at my factory with an industrial camera, say like a Basler camera or a Gigi camera or a USB 3, and we can find anomalies in products. Maybe it's bad solders on a circuit board, bad materials, any kind of defect that you could find visually that the human eye could detect. You could also do that with that as well. So this is kind of what the quality management kind of flow looks like. We take an input, we get images to it, we send it to Lookout for Vision. We can run that on our Jetson Edge device, and then use a dashboard to say how effective our anomaly detection is, and then take some sort of action on it. Maybe stop the assembly line or send an alert to someone saying we're getting all these defects that are going on. So any of these things are possible. Here's an example of a Jetson device here. This is one of our partners, AD-Link, makes this. So this has a Jetson Xavier NX inside of this, but it's an industrial form factor. This thing's very tough. It has no fans. It has no way for dust to get into it or anything like that. So these are kind of made for these industrial types of situations. Do what? Oh, sure. Why not? We have a super special guest appearance by a Jetson-powered robot. Well, hello. Hello, Spot. All right. So these are the kind of cool things you can do with these Jetson devices. Simply amazing. He likes applause. That's awesome. Take a bow. Oh, thank you, Spot. That's so awesome. You gonna go down the ramp? All right. Bye, Spot. All right. So we have TwinMaker, we have a RoboMaker service, and these Greengrass things that I talked about. It can help you maintain and deploy these cool robots. And we've got a fellow here, Camilo Buscarone, works in that area. So definitely hit him up if you want to learn more about the robotics side of things. You can instill some knowledge. All right, so there's one more service that I wanted to tell you about here. So talk about AWS Panorama. So that's another service that also runs on Jetson devices. And what does Panorama do? So what it does is it really gives you a way to have a platform to deploy securely applications that monitor RTSP video streams. So say you're in a situation where I need to monitor security of a premises or maybe a retail setting, and I want to be able to run my own models on those edge devices and applications, but maybe I don't necessarily trust where they're mounted, and I need those things as hardened and secure as possible. I can use a Panorama device to do that. So we have two different devices that we offer. We have an AWS one that's powered with an AGX, and then we also have one here. This is a one by Lenovo that's an NX-based one. So can't run quite as many models. The price point's a little bit lower, but you can plug this in as long as it's on your Ethernet network. And your RTSP cameras can talk to it over TCP/IP. You can run these models and deploy these to the edge using our Panorama platform. So again, there's kind of two different spectrums of use cases. Jetson's powering most of these to run on the edge reliably with good performance. So how does that work? So let's talk a little bit about how Panorama works, right? So you build your models on SageMaker. That we have a simulator you can run and test those models out without ever needing an edge device. So you can kind of see how they're working and performing and debug your code in, say, for example, a notebook. And then once that's ready to work, we go ahead and we can import our model to an application on the Panorama platform. And from there, we can go ahead and deploy that code and service APIs out to your edge devices. And again, you can deploy things in groups or fleets, and you don't need to worry about all of the nuances of managing the operating system. AWS will do all of that for you. So it's taking away a lot of the heavy lifting of managing a platform manually and deploying it out to the edge. And all you need to worry about is your applications and your models. And so as long as you're using the Panorama SDK, which you can use TensorRT or SageMaker Neo to run those models plus your code, then you're good to go. And then you can send data back as far as inference and things like that back to AWS, and again, take action on it, log things, and put things in time series data to monitor your drift as well. So same type of thing there. So I wanted to open up now for questions. So let's go ahead and have Eddie and Yushin come up here so we can get questions answered. We want to make sure we had plenty of time for y'all to get that. All right, so if you have any questions, you can either come up to the microphone here, or I'll try to hear you and repeat back to what people have. So. Any questions? No?
What was which of the devices was it you were using for that particular demo?
For the particular demo of the video in front of my house, that was running on a
Jetson Nano, I think. We tested on Jetson Nano and it works. It's just a single stream, and Jetson Nano is able to handle that. But if you're looking at, from our experience, if you have around 5 streams, then NX would be a good choice. If you handle around 5 to 10 or even more than 10, then definitely go with an AGX. Or I think it's a normal IP camera.
I think the standard ring stream was 720p, I believe, is what I pulled from the stream directly, and then we just assembled that video out of the little bits.
If you're talking about the inferencing time, so DeepStream has the first layer. In the first layer, it has the resize capability. So when we actually run the inference, the size of the pictures are around 224 by 224. So we shrinked it down, and it's all handled automatically or by configuration through DeepStream application.
Anyone else? Am I missing anyone? It's kind of hard to see with the lights here. But.
Anything else?
Okay.
All right. Well, thank you everyone for coming. We appreciate you spending your time out of your busy day here at Remars to come out and listen to us. I hope everyone learned something, and thank you.